Okay, everybody, moving on to the second last unit for the year, and this is redox and electrochemistry, or otherwise known as oxidation reduction and electrochemistry. And here in this unit, we examine the role of electron flow in chemical reactions, and we look at how those transfer electrons can then be used to create electricity, and then what's that role of going forward to create electricity and then backwards or in reverse to take electricity and force chemical reactions to take place. So it's a very interesting unit. It's going to be a quick one, but let's look at some topics that you need to know. And the reason I'm rolling out these topics is the bottom line here is you really need to know each skill before you move on to the next one. So assigning oxidation states then states, feeds into each of these reactions, and each one feeds into the next one. So it's important to know that as you check these off, that you know how to do the previous step. And if you know how to do that, then this becomes a lot easier. So I urge you to go back and fix things if you're misunderstanding, or contact me, or find another way to understand it, and be attuned to that as we move. All right, so in the beginning, we take a look at the terms oxidation and reduction, and we start by going way back in time to 1800, when Alessandro Volta created the first battery. Okay, and again, a battery is a device that we know produces electricity. And he did this using zinc, copper, and salt water, and he stacked them in this little thing where you could see he's got this almost little tissue paper here, or this like he soaked this tissue paper really in salt water, and then he had these stacked zinc and copper slugs, or these discs, and he would pile them up and alternate the zinc, the copper, the zinc, the copper, and he had salt in between them. And then when he put this together and he added a wire to it from one side to the other, he found out that electrons would flow, or electricity would be created, a voltage would be created that was creating this circuit. And the electrons would flow out and then back in and create some type of, voltage here, or some type of electric flow. And it was a constant electric flow. So it was the first time that, a constant flow of electricity was noted using a chemical reaction between these copper and these zinc. You can see the copper is this orange-colored metal, and the zinc would be this light-colored metal, and then this salt water barrier. Later, the electric energy from these cells, these electrochemical cells, were used to decompose compounds, which eventually, scientists were able to isolate some new elements and put them on a periodic table. So an interesting story. So really, they call this a voltaic pile, because you piled up these disks and then create electricity using this battery. Now, of course, this is very crude, very large device. Now we have batteries that are all types of different ones. So we wanted to use the term oxidation, okay, and reduction. Now, oxidation typically, a long time ago, historically meant reaction with oxygen. So as long as you reacted with oxygen, you were oxidized, and we still use that today. So what we need to do is first track whether or not something has lost or gained electrons. And the only way we can do that is by looking at something called an oxidation number. So this number simply tells us whether an atom has lost or gained electrons from its neutral state. Okay, and it's often the charge on the element. So I wouldn't really go into any deeper than that, or the assumed charge on an element. Okay, and it makes it easier for us to track electrons. So basically, you kind of already know this, but when you look at the charge, this number up here would be called the oxidation number. So the oxidation number of nickel 2 plus is 2 plus. The oxidation number of iron is 0. So keep in mind that the oxidation number of an element alone, or an isolated element, or a free element, sometimes they call this a free element, the free state. Okay, the oxidation number of a free state element is always 0. An element that's written alone is neutral. Okay, and it's a neutral oxidation state, or oxidation number. All right. So in this case, if you were to find the oxidation oxidation numbers of all elements in this reaction, in iron plus oxygen is iron oxide. Again, we're looking at the oxidation of just that element. We're not counting the coefficients. Remember, coefficients are simply multipliers. Okay. The coefficients are for the balanced reaction. They are not related to the oxidation numbers. Okay, so the oxidation number of the free element here, it's by itself is 0. Okay, oxygen is by itself here. It's alone. It's not in combination with another element, 0. Okay, so again, and I'm looking at this. So if I know the oxidation number of oxygen is -2, and there's 3 of them, okay, that would be a -6. I know that I need a +6 here to make 0. Remember my slice and dice. Okay. Again, we're not going to worry about the 2 here. We're not going to worry about the 3. We're not going to worry about the 4. All right. And I know that there's 2 irons, then each iron must be +3. So these would be the oxidation numbers, the oxidation states of those elements. Crucially, you get that right. All right. So again, that would be my oxidation numbers. Okay. Now, a couple of things. If you have a 0 and then you go to +3, that means the oxidation number has become more positive, and that means you've lost 3 electrons. So 3 electrons have been lost by the sample. Okay, if you have a 0 state, okay, that goes to a negative oxidation state. That means you've gained electrons from neutral. Okay, and then so you've lost 3 electrons, and this means you've gained 2 electrons. Okay, from neutral. So that means you've gained electrons. So the change in an oxidation number, the change in an oxidation state is very crucial because it tells us where the electrons are coming from. We've lost electrons and we've gained them. So if you see that iron has gone from 0 to 3+, it has lost electrons. Well, oxygen has gained the electrons, right? And all the coefficients do is simply make that equal. Okay, so we can define 2 terms. We can define oxidation. And oxidation is, again, used to be the term that would allow us to, oxidize or react with oxygen. But if you do react with oxygen, you actually lose electrons. So oxidation from our for our language going forward is going to be the loss of electrons. Anytime you undergo oxidation or you've been oxidized, you've lost electrons. Okay, and what happens is this oxidation number rises. It goes up. It becomes more positive. And when it increases, it becomes more positive. Okay, you could think of it that way. Okay, that becomes oxidized. All right, more positive. Okay, and reduction is the gain of electrons, and the oxidation number decreases or becomes more negative. Okay, now more negative doesn't mean it always becomes negative. It becomes more negative than it was before. So in the case of oxygen, oxygen gains electrons, okay, and it becomes reduced. Now I know sometimes the word gain and the word reduced or reduction sounds a little strange because it sounds like you're kind of being counterproductive here. But a gain of electrons is a reduction in the oxidation number, which means the number is actually becoming more negative or going down. Think of it like going down. All right, so reduction means to gain electrons. Oxidation means the loss of electrons. All right, so that's important to know. All right, now to make it a little bit easier and to look at some rules on how we're going to do this, okay, is we're going to look at some rules quickly on how we look at oxidation and reduction. Okay, number 1, some rules on how to assign these numbers. How do we know how to assign these numbers? Well, if you're an uncombined element in the free state, okay, is 0. Again, uncombined means free state. Okay, so any element in the free state is 0. Okay, the oxidation state of a monatomic ion. Monatomic means one atom. One single atom ion is its charge. So, for example, nickel 2+ and Fe0, right? Fe0 would be 0 by itself. Nickel 2+, the oxidation state is its charge. Okay, oxygen is usually going to be -2, except in peroxide when it's -1. So the peroxide ion is going to be this. That means oxygen is -1 in peroxide. All right. In a binary compound, again, binary compounds have 2 elements in them. Okay, the higher the electronegativity element has the negative oxidation state. That's important to know. So if you have a sample like HCl, Cl has the higher oxidation, higher electronegativity. That's going to have the -1. This would be the +1. Okay, for compounds, for any compound, the sum of the oxidation states must be 0. We know that from our formula units. Okay, when we did the unit on formulas and crisscrossing. Okay, compounds must be neutral. Okay, that's something we need to know. Okay, for polyatomic ions, all right, that have charges already, this charge goes for the entire molecule. So the sum of the oxidation states must equal the charge on the ion. For example, sulfate, the sum of the S and O's together must equal -2. All right, so that's going to become important to know. So again, the -2 does not go for the oxygen. It goes for the entire molecule, the addition of the oxygen and the sulfur. Again, so we'll get used to doing that. All right, so some examples of finding the oxidation number. If you want to find the oxidation numbers, we'll simply, you can either uncrisscross them or you can do a slice and dice, okay? Again, we'll do a few of them. Let's just say I slice this and make it equal to 0. I look at the periodic table. I know chlorine's -1, okay? That's my oxidation state from the table. But in the compound, you must have the sum of them, all of them must be equal 0. So there's 2 chlorines. So -1 times 2 is -2. Calcium must be +2. So those are your oxidation states. Very important. So oxidation numbers would be that guy and that guy. Okay, not the bottom. This is the sum at the bottom. Okay, NaOH is an interesting one. We'll cut this up a little bit. Okay, we know that oxygen is usually -2. Hydrogen is -1 in the base. Okay, so that means +1 must be for these guys. So that's equal. That's easy to know. So +1, -2, -1. Okay, bromine by itself is written at 0. Gold by itself written 0. Potassium nitrate's an interesting one. If I take potassium nitrate and I separate this into my zeros, right? If I take a look at oxygen, we know oxygen is -2. There's 3 of them for a total of -6. That's fine, moving along nice. Now, here's the weird part. If you try to look up nitrogen, you can see nitrogen, you really don't know what it is because it's got many positive and negative states. So you really don't know. So what we can do is we can use the other element, the potassium, which we know is +1, okay, to determine what that X is. So +1 and -6 is -5. Remember, you got to make 0. So the only way that this will work is if nitrogen is +5. So +5 becomes my oxidation state of nitrogen in this case. So those are my oxidation states. Okay, copper chloride's kind of easy. Again, we know what chlorine is already. That's a -2 at the bottom because 1 times 2 is -2, and that would make copper +2. Again, we can't do copper first because copper has more than 1 charge, just like nitrogen does. All right, so these are my oxidation states, and not last but not least, nickel sulfate. Okay, again, oxygen -2 from -8. You can't do sulfur first because it's got a choice. And nickel has a choice. So we're in a little bit of a bind here. So like, what are we going to do if we don't know these? There's a little trickery. What we can do is take a look at the sulfate ion. The sulfate ion has a charge of -2, right? So we could take the sulfate ion itself, okay? Remember the charge, the total charge has to be -2 here according to rule number 6, okay? We know oxygen is -2. So that's 2 times the -4 is -8, which makes sulfur has to be +6. So sulfur in the sulfate ion has to be +6. So we can use that with a +6 here and the +6 oxidation state at the top. So that gives me a -2 at the bottom, so that nickel must be +2 for its oxidation state here. So we can use this little trick on the side to help find this. Okay, so that sometimes you may have to do that as a result. All right, so that's finding your oxidation state. You must be able to find oxidation state to do the next part. All right, so next part coming is take a look at our reactions really quickly. And this is a little memory device to help you learn, okay, and help us remember the what oxidation and reduction means. I like to think of this as the ground floor. This is going up to the higher levels, and this is going down the basement. So think of the ground floor of a house as being 0 elevation. You go down steps or you go up steps, okay? And I want you to think of oil rig. Oxidation is losing electrons, and reduction is gaining electrons. So oxidation is losing, reduction is gaining. And I like to think of the oxidation number going up for the I on oil, and the oxidation number going down for the arrow on the I for the rig. All right, so oxidation is up, reduction is going down. So as long as you go up on this number line, you'll be oxidizing. As long as you go down, you're reducing, and you're going to watch this oxidation number. So oxidation, there's a couple things about oxidation and reduction. They must occur together simultaneously. One's not going to occur before the other. They basically occur at the same time. Okay, electrons are going to flow from the one that's oxidized, because it's going to be the loss, to the one that's reduced. Okay, again, that's a gain. So we're flowing from, the electrons will flow from one that's oxidizing to the one that's reduced. Okay, the following are redox types of reaction. Again, the word redox comes to the idea of oxidation and reduction. So that's how we're going to do this. So the following are redox reactions. And again, we looked at 5 types of reactions. We looked at your combustion. We looked at our single replacement, our double replacement. We looked at our synth. Okay, and we looked at our decomp, right? We looked at our decomposition. So we had these 1, 2, 3, 4, and 5 reactions. Okay, 4 out of the 5 of these guys are going to be oxidation reduction reactions. Okay, so single replacements are redox reactions. Okay, synthesis, decompositions are redox type of reactions, and combustion reactions are redox type of reactions. Okay, because again, in these single elements, okay, and compounds, okay, are involved. So if you have single elements that are becoming compounds and compounds becoming single elements, you know those charges are going to change. Okay, double replacements are not going to be redox, because all you're doing is moving ions around. Okay, not redox, you're exchanging ions. So because you're exchanging ions that are already there, you don't have an electron motion. All right, so you don't have a change in oxidation number. So it's important to know. Okay, so let's practice this. Let's label these as becoming oxidation reduction. We can use our chart. All right, let's just say I have a 0 going up to 3 plus. If I have 0 on my chart, I'm going up to 3 plus, I must be oxidation. Okay, if I have P0 and I'm going down to minus, I must have gained 3 electrons, I must be a reduction. So this would be a loss, this would be a gain. Okay, again, we're going from 0, more negative. I'm going down the chart. Okay, let's just say I'm at +2 and I go to +7. Well, that's going up, right? I'm losing electrons. That would be oxidation. So this would be a loss of electrons, becoming more positive, going up the chart. Okay, and again, you don't have to use this. It's just a good way to think about it, like in a more of a physical way. Let's just say I have -2 for sulfur and I go up to +2. So I'm becoming more positive, which means I must be losing electrons. All right, so I must be in oxidation. I lost electrons. It's a loss. Okay, and again, let's just say I have a -1 and I go up to 0. That means electrons are being lost by the system. And again, we can balance this too. There's 2 electrons here, two chlorines here. There must be 2 chlorines here. You must be losing electrons. Again, would be a loss of oxidation. And last but not least, let's just say I have a +5, which would be off the chart, but up here, and I was going down to 1, I would be losing electrons. Gaining electrons, become more negative. Okay, I would be reduction. Remember, when you gain electrons, become more negative because electrons are negative. Okay, and this begs for a little bit of a strange way to think about this. Okay, is thinking of one helping the other. So if something loses electrons, so if you take a look up here, if something is losing electrons to something that is gaining them, then the one that's gaining them must be helping the one lose, and the one that loses must be helping one gain. So again, these have to work in tandem. They have to work together. So one is an enabler of the other. One is helping the other. So what we kind of do on this is we label something called an oxidizing agent. An oxidizing agent is that is reduced because something that's reduced helps oxidation, right? So you're an oxidizing agent if you are actually reduced, okay? And many times that's going to be active nonmetals. Okay, active nonmetals are good examples of oxidizing agents because these gain electrons, right? We know that nonmetals have high electronegativity, so what they do is they allow other things to be oxidized. For example, oxygen is a good oxidizing agent. Why? Because it gains electrons, so it enables iron to lose electrons, and it would be oxidized, right? So it's an oxidizing agent. And in reverse, a reducing agent is one who's oxidized, all right, because it allows something else to gain electrons, all right? So active metals, those would lose electrons, okay, and be reduced, okay? I'm sorry, and become oxidized, but they allow something else to be reduced. So again, you're gonna have to get used to these terms. It takes a little while to get used to them. I think these are where you might have a little bit of trouble labeling them, but again, with some practice, we're gonna be okay. All right, so that's some of your introductory oxidizing and reducing, ideas and some definitions. Please make sure you can label the following changes in oxidation. You need to know how to do this, and make sure you can assign your oxidation states. If you need to look back over that, take a look at it. But that should be the first beginning lesson. All right, have a great day.